So we're going to review for the final exam. So, like I said before, we're just going to kind of go through each chapter and try to remember what was in those chapters, and we'll go through it. Well, first off, chapter one was super simple because there wasn't very much in chapter one that we had to worry about. So remember, still kind of same thing. I wouldn't worry too much, maybe at all, about chapter one. But basically, we pretty much just focus on the scientific method, where again you have some type of observations that leads to a hypothesis that leads to some type of experimentation, which leads to more observations, maybe some refining of a hypothesis. Remember, that could kind of end up in one of two places, can end up with a theory or a law. And remember that a theory is sort of a tentative explanation of what you observed. Uh, it is maybe not right in all aspects, can be later revised. So that's more of a theory versus a law, where again, in a law situation, it always happens the same way, no matter sort of what is the situation. So as we talked about throughout the semester here, for example, Bohr's model of the hydrogen, or Bohr's theory of the hydrogen atom, is a theory that was correct in for hydrogen, but did sort of fall apart as you went to other atoms and other elements. Dalton's atomic theory, right, was correct in some of the aspects of it. Some of the parts of it was later proven not to be so correct. For example, all the atoms of the same element are identical to each other, which, as we talked about with the existence of isotopes, sort of makes that part of his theory not correct. A law on the other side is conservation of mass. So, for example, in a chemical reaction, the only thing that happens is we make bonds and break bonds, and we do have conservation of elements. So if we started with four carbons, we will end with four carbons, and that's sort of the law of conservation of mass. Since carbon has the same mass on both sides of the arrow, you will have the same mass of carbon when it's all said and done. You won't destroy anything. So that was the major sort of thing, and like I said, I don't even know if we really have to worry too much about really chapter one. Where we really got into sort of the class was chapter two. And in chapter two, we talked about things like obviously measurements and units. So we started with units. Remember, there are sort of two types of units that we've talked about. There are basically the English units and really the SI units, right? And the SI units are sort of the standard uh, international system of units. It's really sort of based off of the metric system, which is pretty much what everybody else uses. And that's usually the units that we use here in chemistry. Remember that different units do represent different things. So obviously, if we have something like a kilogram, that is representing a mass. For example, if we have something like a liter, that represents volume. If we have something like Kelvin, that represents time, and so forth. So we have these different types of units. The SI units, again, are essentially the ones that sort of won out in the race there of different types of units, which is really our metric system. In addition, with metric type units, remember that we do have certain sort of prefixes that are used to sort of change the meaning of it. And remember that we want to make sure that we kind of use those things correctly. So, for example, if you had kilo and that was 10 to the 3, remember that when you do see something like that, that if you're looking between, say, kilograms and grams, that when you look at this number, that is how much there is in the base unit to one of the prefix units. So in 1 kilogram, that would be 10 to the 3 grams. And remember, not the opposite way around, which is very common that people sometimes do. Or if you had something like nano, which is 10 to the minus 9, that would mean, for example, in 1 nanometer, the prefix unit, there are 10 to the minus 9 meters. And it really doesn't matter, as we talked about, really what the base unit is. The prefix works the same way for anything. If you had 1 kiloliter, you would have 10 to the 3 liters. So again, works the same way. You want to make sure you kind of set it up that way correctly as well. Now, when we look at these, remember that when we do see 10 to the minus 9 or 10 to the 3, that is really 1 times 10 to the 3, which is scientific notation. And we did talk about, obviously, in that chapter, scientific notation. And remember, that is a way to write big numbers and really small numbers in this sort of setup where this is a number between 1 and 10. And obviously, this is a number that's either going to be positive or negative, depending on which way you need to move your decimal point to reach a number between 1 and 10. So if we had, again, 0.00562, we go 1, 2, 3 places to the right, 5.62 times 10 to the minus 3. And obviously, if we had a bigger number, we would go to the left 1, 2, 3 places, 4.4236 times 10 to the fourth. Probably more important with scientific notation, as we talked about, and we still talk about it to this day as well, is making sure, again, that when you do punch it into your calculator, right, we do use our exponent button, right? And on your calculator, you have that button, or again, an EXP button, and some calculators have a times 10 to the end, but the calculator for here uses this one. And that is what we want to use whenever we're putting a number in our calculator scientific notation. So if we did have something like 4.5 times 10 to the minus 6, to punch it into our calculator, we would go 4.5, we would hit our exponent button, and then we would hit our negative button and 6. So more importantly, again, than maybe writing in scientific notation is being able to punch these things correctly into your calculator to get it into scientific notation. Now, one of the major things that we did talk about sort of in this chapter is obviously measurements and how to take proper measurements. And remember that when we do take measurements, there's always some sort of uncertainty associated with your measurement. And when you look at the measurement that you take, the degree of uncertainty is dependent on the piece of equipment that you're using. So remember, if we had something like a ruler here, and again, these were centimeters, and we wanted to measure our arrow here. Remember, there's two types of sort of numbers that you typically see on an instrument that you're using to measure. There's usually numbers that are markings that have numbers associated with it. So usually, again, there's these markings with numbers, and these are sometimes referred to as our large markings. And in this particular example here, we have 1 and 2. The difference between that is 1 centimeter. Then there usually is markings that do not have numbers, but they do fall between those two larger markings. So remember that you want to start counting past the last big marking. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And you want to stop at the next big marking, which is 10. And since there is 10 markings between our large marking of 1 centimeter, 1 divided by 10 will tell us that each of those little markings again represent 0.1 of a centimeter. So that is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, and 1.9 in this case. So when we do take a measurement, remember that there is always numbers that no matter who is looking at it, everybody really should agree and give sort of the same reading. So clearly in this case of my example, my arrow is at least 1.4, and we would want to record that. And once again, remember that that is what is sometimes referred to as all the certain numbers. And once again, these are the numbers that there really should be no disagreement about. The estimation or uncertainty in the measurement comes next because again, we can see that my arrow is not exactly 1.4, it's not exactly 1.5. So that's where we have to sort of guess. And I may look at that and go, looks dead center to me and record it as a 5, along with obviously the units. Again, somebody else may look at it and go, it looks a little less than half, maybe it's a 4 or something like that. And that is our first uncertain number here. And remember that the importance of sort of recording a measurement where you record all the certain numbers plus the first uncertain number, that's important because that is basically what significant figures are. And that would mean, obviously, in this case, that we have three significant figures here in this particular measurement. Remember that we also talk about sort of the tolerance or uncertainty in the measurement that we can figure out. And remember that you can figure out the sort of plus or minus that you're supposed to be putting on your labs by taking the smallest marking and dividing it by 2, which in this case would give us 0.05 centimeters. And that is sort of our plus or minus. And we could record this as plus or minus 0.05 centimeters. So what does this really do for you? If you're not sure how far you should take the reading, it will tell you how far you should take the reading. So that obviously should go to 2 decimal places, which once again is exactly where we took our particular reading to. Remember again that the scale does change, but typically speaking, as we've talked about, you could typically take a measurement to one more place to the right of the smallest marking. Remember, it's not 100% of the time that's the case, but most of the time that is the general rule you could happen. Remember, though, if you had something like we saw in one of the lectures where we got I run out of room there. Let me make my graduated cylinder a little bit bigger there. Just need to increase it there. There we go. And I'll go up a little bit more. And then that'll be 18 and then 20. So once again, in this scaling, our big markings are between 10, and if these were milliliters, our large markings here are going to be 10 milliliters. Our small markings in this case are going to be uh, 2 milliliters, as there is basically 1, 2, 3, 4, 5 markings in between. So if we divide that, that's going to give us a small marking of 2 milliliters. So once again, if you do find yourself kind of falling between two numbers in this particular scale, that's 18 and 20, which means the best we could do in this case would be 19 milliliters, with our uncertain number being the 9, and we have two significant figures. So most of the time you can go one more place to the right, but again, there are certain times where you may not be able to do so, and this is an example of that. Any questions on how to take measurements? Hopefully that's familiar still. Um, let's see here. So speaking of significant figures, we obviously got into talking about significant figures, and remember that rules of counting significant figures. There are basically a few different types of numbers. All non-zero numbers are significant. Uh, and then when we get to zeros, that is where things get a little tricky depending on the type of zero that you got going on. So remember, there's basically three different types of zeros. There is the leading zero, which is not significant. And those again are all the zeros that come before we hit the very first non-zero number, and they would not be significant. So in this case, this would have again three significant figures, the last three ones. There is the trapped zero, which is basically going to be significant, and that is a zero that is trapped between two non-zero numbers. So in this case, this would have four significant figures. And lastly, there is a trailing zero, where they are going to be significant if there is a decimal point in the number. So remember that the decimal point doesn't have to be near the zeros or anything like that, but it does have to be actually written into the number. You can't just assume that it's there in the case of significant figures. So again, it has to be actually written in there. So if you had again 600 versus 600 written like this guy would have four significant figures as significant. All these zeros would be significant as they are after the last non-zero, and they do have a decimal point in number. Here, this guy would actually just have one significant figure, and that would be the 6, because again, there is no decimal point that is written in this number. That would mean the uncertainty in that 600 with no decimal point is like saying, I think it's 600, but it could be 700 or it could be 500. There's a big room for lots of error there, as opposed to this 600 here, where you're saying, I think it's 600, but it might be 599.9 or it may be 600.1, which is again a much better sort of measurement there, less uncertainty with that measurement. Now, we did talk about exact numbers, and exact numbers are things that are pretty much done one of two ways. Either they are something that is counted, or it is some type of definition. Like, for example, if you had four pencils on the table, you're just going to count the pencils, so that would be an exact number. Any type of equality that is, say, like 12 inches is 1 foot, that is an exact quantity. Uh, if you had 100 centimeters in 1 meter, that is also an exact number. It is always an exact number if it is something like an English to English conversion or a metric to metric conversion. The only time you do have to sort of look at a conversion that is not an exact number is if you kind of cross over. So if you cross over from like English to metric unit or vice versa, whichever way you're going, you do need to look at the significant figures there in those numbers that you have. The one exception, or there's a couple that they use here, but one exception is 1 inch is equal to 2.4 centimeters exactly. So that is sort of an exact conversion that they did want you to know. They also used, I believe, here the grams and pounds, if I'm not mistaken. Let me find that there. I think they did. 1 pound is 454 grams. I think they used here. Actually, I think they might have used the real number here. I think. Might look that up. I forget which number they used here. I think it was. Yeah, 453.6 is what they use. 453.6. And there was a couple others, like 1 mile is 5,280 feet. Remember, these are things that you expect you to know. 1 kilogram, 2.205 pounds, and 1 liter is 1.06 course. So these are some of those sort of exact conversions or conversions, not necessarily exact conversions, but conversions that you do need to know. These here are sort of our exact conversions. But these are also some conversions that you do need to know. So what is the deal with exact numbers? The deal with exact numbers is because they're counted or considered a definition, They basically can have an unlimited number of significant figures because of that. And really, where that comes into play is when we do calculations. And when we do calculations, obviously, we want to give our answer the proper number of significant figures. And there are a couple of rules that we follow when we're doing calculations. So, calculations with sig figs. And we can either multiply or divide. And again, when we're multiplying and dividing, we're looking at the number of sig figs, and it is the one with the least number of sig figs is what your answer should have. So if you multiply 1.23 times 2.1 times 1.333, here we're multiplying 3 sig figs there, 2 there, and 4 there. That means our answer should have only 2 sig figs. Remember that the least number of sig figs, or even the smallest decimal places, are essentially your worst measurement, and your calculation can only be as good as your kind of worst measurement. So that's the one that limits how good it is. Again, when we add or subtract, we are looking at decimal places. And again, it is the one with the smallest number of decimal places is what your answer should have. So if you added 1.444 plus 2.1, you get 4453. Here, 3 decimal places, 1 decimal place. We should come here to 2 decimal places, or 1 decimal place. I'll spit that out. Got too many numbers in my mouth. Uh, 1 decimal place, which would take us to 3.5. 3.5 has 1 decimal place, but it does have 2 significant figures, which may be important if you continue on with your calculation. So a couple of things we talked about, obviously, if you're doing multiple steps in a calculation, you definitely don't want to round your answer to the very end. And you do want to kind of keep track of your significant figures as you're going through the calculation. Again, if you combo a couple of things together, you do want to kind of follow it all the way through and see where you end up in terms of your answer. Any questions on that there? Now, let's see here. So we got sig figs, sig figs. The other thing we talked about was scientific notation and in relationship to significant figures. Remember that when you do write a number in scientific notation, the way it is written, all the numbers that come before the times 10 part are always significant. And that means in this particular case, it has 3 significant figures. That is one of the sort of benefits of writing numbers in scientific notation is you essentially can control how many significant figures you want, because there can come a time when you do a calculation and you need to give the answer to a certain number of significant figures, and there may not be a way to do that in just regular sort of decimal form. The only way to kind of do it is in scientific notation. For example, here, if I just needed 2 significant figures, I could just write it as 4.1 times 10 to the minus 3. That would now have 2 significant figures. If I just needed 1 significant figure, I could write 4 times 10 to the minus 3. I now have 1 significant figure. So you really can sort of almost control the number of significant figures by writing a number in scientific notation to see what you end up with there. All right, so it's sig figs. All right, so let's take a look then at some other things that we talked about in this chapter, and probably one of the most important things that we talked about was dimensional analysis and how to set up problems, which hopefully you are doing. So dimensional analysis is the way where we use an equality like 12 inches equals 1 foot. And we can turn any equality into conversion factors where you could go 12 inches over a foot or 1 foot over 12 inches. And we could use these conversion factors to set up our problem. So if we had 45.6 inches and we want to know how many feet that was, the purpose of dimensional analysis is to set it up in a fraction sort of calculation where there's a top and bottom. So this right here isn't really a fraction, but we could put it over 1, and that gives us sort of our top and bottom. And we can see our units that we want to get rid of are up on top. So remember, opposites cancel. So we would want to use our conversion factor here to the right. That puts those same units on the bottom in the opposite location. So 12 inches is 1 foot. Remember that when we dimensional analysis, the math is also done for you in a sense. It's always the same math, which is we are multiplying the top and dividing the bottom. In this particular case, we end up with here 45.6 divided by 12, 3.8 feet as the inches cancel in this particular case. Now, in terms of significant figures, again, in this calculation, whenever you set something up in dimensional analysis, you are always multiplying and dividing, which means you're always looking at just the sig figs. This is an exact number, so we would not worry about it since it is an exact number. We would go back here actually to this number, and this is actually the number we have to worry about, which means it is 3 significant figures. And because of that, our answer actually should end up with 3 significant figures here, which means we actually do need to actually pop a 0 on that to sort of have it to the right number of significant figures in this particular case. Now, like I said, in most cases, if you come across a conversion factor, it's probably going to be an exact number. Remember that the only time that we don't worry about or have to worry about sort of conversion factors is if we cross over from sort of the metric system to the English system. So, for example, if we had something like do liters and quarts. So 1 liter is again 1.06 quarts. So we have our metric, we have sort of our English units. And if we were going to use this in a sort of calculation, let's just say we had 52.56 quarts, and we want to know how many liters that would be. Again, we would set this up. And again, you can kind of put a 1 over if it helps you. Quarts are on top. So we would need quarts on the bottom here and a liter up on top. Multiplying and then dividing. Quarts will cancel and will get us, in this particular case, 52.56 divided by 1.06. That's going to give us on our calculator 49.5849056 liters. Here we do need to look at this conversion factor, and it would have 3 significant figures. We would look at our original number that has 4 significant figures. That means technically we should end over here at 3 significant figures, 49.6 liters in this particular case. So if you are using any type of conversion factor that is an English to metric crossover, except for like the pounds and feet or inches and centimeters, you do have to take that conversion factor into account when you're doing it so that you get the right number. Again, if you're doing multiple steps and you're sort of getting an answer in between each step, remember you do not want to sort of round until you get to the end. You want to kind of keep track of everything, keep a few extra digits so you don't end up with any type of rounding error that definitely could occur. Now, the other sort of things that we did talk in this chapter that was important was temperature and temperature conversions. Remember, there's three types of temperature scales. There's degrees Fahrenheit, degrees Celsius, and our good friend Kelvin. And as you've experienced, Kelvin is pretty much our major unit we use for temperature in chemistry. And we talked about how to kind of convert between these or calculate each of these. So if you have the temperature in Celsius and 1 Fahrenheit, temperature in Fahrenheit is 1.8 times the temperature in Celsius plus a 32. If you want Celsius, that is the temperature in Celsius is equal to Fahrenheit minus 32 divided by 1.8. You could also get Celsius by taking the Kelvin temperature and subtracting 273.15, and that will get you your Kelvin as well. But probably out of all these here, once again, it is Kelvin that is probably used the most. And here, our temperature in Kelvin will equal our temperature in Celsius plus a 273.15. Remember, they do want you to kind of use that whole number there at this school here to calculate Kelvin, and then obviously going backwards would be right there. Remember that when we do calculate temperature, it is the one place where we typically do not follow super strict significant figure rules. So the general rule is if all you're doing is a temperature to temperature conversion, then whatever the original temperature value looked like, what that means is if it was a whole number or it went to the first decimal place, second decimal place, when you do your conversion, that is what you want to keep it the same number of sort of decimal places as it was when it was installed. And that's typically what we do with temperature here. Questions on temperature there. Now, one of the last things we talked about in chapter 2 was density. And density is the measure of mass to its volume. So we have D is equal to M over V. We can rearrange this formula and solve for any of that. So V is equal to M divided by D, and mass is equal to the volume times the density. So those are three ways to rearrange it. Remember that density basically has some popular units, which are grams per milliliter, are grams per cubic centimeter. And these are the typical units associated with solids and liquids. And and remember that 1 milliliter is the same as 1 cubic centimeter. So it is a one-to-one conversion between that. Now, one of the things we did talk about was different ways that we get volume. And the different ways that we can get volume here is pretty straightforward. We can either take a volume reading. So that's probably very common. Just, kind of look at something and read the volume. Also, we can do a very common procedure, which is volume by displacement. And that is when you have an initial volume of a liquid like water in a container. You take some type of solid and you dump it in there. When you do so, the solid will displace some of its liquid, and it will make the liquid basically rise. So I'll just kind of bring it up here. And we will end up with a final volume. So if you subtract the difference between the two, the volume of the object is equal to the final volume minus the initial volume. And that's a very common way that you could get the volume of an object. We did an experiment with that with some rubber stoppers. We tossed it into the water and took a reading, and you could get the object's volume by doing that displacement. We don't talk too much about it in this class, but a reminder that typically with gases, the units of density are usually grams per liter is typically what we got going on there. So I think that is chapter 2, if I'm not mistaken. All right, so after chapter two, we traveled to chapter three, which was about matter. And remember, there are three states of matter. There is solid, where everybody's packed in fairly tight to each other, not a lot of energy happening. We obviously have our liquid state, where we still have things relatively packed into each other fairly tightly, but they actually have a little bit more energy, and that's why they're able to sort of pass each other, the atoms and the molecules, and that's why we associate liquid as being a fluid sort of state. We have our last state, which is gas. At that point, everybody has basically broken apart from each other. They're flying around. That's what causes the pressure we associate with gases. We also talked about sort of the transitions of state that occur and what's going on in those. So remember that as we go from solid to liquid, that's the process of melting. As you go from liquid back to solid, that's the process of freezing. As you go from liquid to gas, that's the process of evaporation or vaporization. As you go from gas back to liquid, that is condensation. You could also go solid, skipping the liquid cleanup and go directly to gas, and that is known as sublimation. Could also go from gas directly to solid, also skipping the liquid part. That is deposition. Remember that melting and freezing occur actually at the same temperature. So, for example, for water, that is 0 degrees Celsius. What is important at that temperature is what you're doing with energy. Are you putting energy in? Are you taking energy out? Remember that, for example, for water at exactly 0 degrees, you have both phases happening at the same time. You have like ice crystals. So you got some solid water, you got some liquid water happening. It's not until you get a little bit above zero that you transition to liquid water, not until you a little below zero that you transition to ice. Same thing at the evaporation and condensation sort of transition also happens at the normal boiling point of a substance. And for example, for water, that's 100 degrees Celsius. And at exactly 100 degrees Celsius, again, you still have the both phases happening, the liquid phase and the gas phase sort of happening together. Now, in terms of energy, as we go from solid to liquid to gas, those are all processes where energy has to be absorbed. And as we've talked about, when energy is absorbed, that is what is referred to as an endothermic process. And if you're going in the opposite direction, going from gas to liquid to solid, the gas molecules will have to lose energy, and energy is released in this process. And that is what is known as a exothermic process. As the gas molecules release energy, they no longer have enough energy to sort of pass one another, so they kind of stick together. And as they continue to lose energy, they start to slow down and they sort of lock themselves up into a more of a solid state. In this chapter, we also talked about different types of properties, physical properties and chemical properties, and physical changes versus chemical changes. And remember, with a physical change, what you start with and what you end with is fundamentally the same thing. So, for example, if you took an ice cube and you melted it into liquid water, they are both fundamentally H2O. There is no change to the fundamental composition of that substance, and that is a physical change. Most common type of physical changes are those phase changes as you go from solid to liquid, liquid to gas, and all around. Those are very common. In a chemical change, what you start with and what you end with are fundamentally different things. So, what you start with and end with are different. So, for example, if you took hydrogen gas plus some oxygen gas, you make some water in this case, balance it. And water is fundamentally different than both of those guys. You cannot get back the original components by any type of physical means. You could freeze the water, you could heat up the water. You will not get back the hydrogen gas or oxygen gas without some type of physical change occurring. So that is the difference between a chemical change versus a physical change. And usually chemical changes are referred to as reactions or chemical reactions in that case. Now, in addition to that, we also talked about elements, compounds, and molecules. And remember that the elements are the basic blocks of everything, like hydrogen, oxygen, nitrogen. Remember that different combinations of these elements will come together to make different compounds. And remember, there is a difference between molecules and compounds. Remember that a molecule is a basic definition of two or more atoms together. And that could be two or more of the same or different. So, hydrogen, the way it naturally comes, is two hydrogen atoms together. That is a molecule of hydrogen. Water, the way it comes, a hydrogen, an oxygen, and a hydrogen. So, it's definitely multiple atoms together. So, those are all molecules. Now, the difference between a molecule and a compound is the compound has to be different elements involved. So, you need a combo of two or more atoms of different elements. So H2O is a compound. It is also a molecule, but again, it is not a element. While H2 is an element, it is also a molecule, but it is not a compound because again, it only has hydrogen in it in that case. Now, we also talked about in this chapter substances, and pure substances are when you have only one substance by itself, it's nothing else mixed with it. So, a pure substance is one substance by itself. So, if you had pure water, that is a pure substance. There's nothing else mixed with it. If you had just pure sugar or pure iron, there's nothing else mixed with it. Now, when you take two or more pure substances and you mix them, you get a mixture. One of the important things to remember again about a mixture is it is actually a physical change. So, what that means is um, what you start with and what you end with are still the same. And also, both parts of a substance will basically retain their identity. So if you took salt and you added it to water, these are both pure substances. When they come together, you get salt water, which is a mixture. And they both retain their identity. And you know that because, again, if you took salt water and you basically had water molecules around a salt, like so, and you heated this up and warmed it up, what's going to happen is our water will evaporate, kind of like what you did in the evaporating dish in those earlier experiments. And you could technically collect that, and then the sodium and the chloride would come back and we would get the salt back. So remember that although they are mixtures, it is not a chemical change, it is a physical change. They maintain their identities. You could actually, through physical means, get back both parts of a mixture. The two types of mixtures we talked about is the homogeneous mixture, and that is when everything mixes, everything looks the same throughout. And we also have heterogeneous mixtures. And these heterogeneous mixtures will not mix together. You can mix it as much as you want, but they basically will separate out into different layers. You'll get some different layers happening. Exactly. So, for example, if you mix, as you just said there, if you took some oil and some water, you will have a layer of oil and you'll have a layer of water, and they definitely will not mix. As opposed to if you took the salt and water together, you'll get salt water that will just look like one layer. Everything dissolves, the salt dissolves in it. So homogeneous, heterogeneous, homogeneous, everything looks the same, everything mixes really well. Heterogeneous, we see these different layering happening. You could definitely see different things happening. Now, regardless of the type of mixture that you are dealing with, you can still separate them out through physical means. The two popular physical means we talked about is filtration. And filtration, like we have done in lab before, a little funnel, some filter paper. And that's a really good way to separate out a solid from a liquid, because when you dump that in there, the solid's going to get trapped up there on the filter paper. The liquid would go through there. So, for example, when you had like a precipitate with water, or if you had sand and water. So if you took sand and water, you would put it through the filter, the sand would get trapped up on top, the water would come through, and now we have separated out that mixture pretty easily. Even with a homogeneous mixture where you take something like salt water, as we talked about, you could do a much fancier process, which is known as distillation, where it's kind of a closed environment connected by a really, say, cold tube. And if you take your salt water and you put it in one side and you start to heat it up, that's going to cause the water part to basically dissolve and evaporate, and it has nowhere to go but through this tube. And now, once it goes through this really cold tube, it will go through condensation, and that liquid water will come back over here to the other side. If you continue this process, you will basically evaporate off all the water. You'll be left with just the salt residue on one side and basically the water part on the other side. So even something like salt water, which when you look at it, looks completely like one substance, nothing else in there. Um, you definitely can get back both parts through this process of distillation. Any questions on that? All right, good starting for